This video is on section 3.5, notes, rational functions, and inequalities. And what we're going to be doing first is looking at some different characteristics of rational functions that are unique to rational functions. Most of them are unique to rational functions. And then once we can find these different characteristics, we're going to use them to sketch the graph. So the first we're going to talk about is asymptotes, which hopefully you've heard of before. And typically the definition you get in high school is that it's an imaginary line that the curve approaches or gets close to but doesn't cross. And that's not entirely accurate. An asymptote can be crossed. It's just more rare. It doesn't happen all the time. So we're going to write down the definition of an asymptote over here. An asymptote is an imaginary line, and not imaginary as in like imaginary numbers, but as in technically it's not really supposed to be there. You're not really supposed to draw it. You could also write invisible line. It's not going to show up on your graphing calculator. If you were to graph this with technology, you wouldn't see it, but they act as guidelines, and so we're going to draw them in on a graph dotted to show that they should be invisible. So it's an imaginary line or an invisible line such that the distance between the curve and the line approaches 0. So, oops, sorry, couldn't see that. So an asymptote is a line where the curve gets closer and closer and closer to it, but it could cross it at some point. Sometimes they cross and then they get closer and closer. Sometimes they cross repeatedly. Those are called oscillating lines, but as they oscillate, they get closer and closer. So we'll see an example later on in this video of an asymptote that gets crossed. All right, so finding asymptotes for a rational function, there are three different types. There are vertical asymptotes, which are pretty much seen in every single rational function, although I suppose there's an example you could think of where there isn't one. And then horizontal asymptotes and oblique or slant asymptotes, which are just diagonal lines. So these are kind of the shortcuts that help you figure out where those different asymptotes are. So the first one says the graph has a vertical asymptote corresponding to the root. So Q of x, they're talking about the bottom. P of x is the numerator, Q of x is the denominator. To find the vertical asymptotes, we're just going to factor the denominator and see what x values we should be excluding. Those are going to create vertical asymptotes. The horizontal asymptotes and the slant asymptotes, or oblique, have a little bit more complicated shortcuts for learning what they are. So we're going to find all the vertical asymptotes for these examples first, and then we're going to come back and find the horizontal and the oblique. So for this first one, we have 2x minus 3 in the numerator, and in the denominator we can factor that. That's difference of squares, so that would be x plus 2, x minus 2. And so for this function, we have two vertical asymptotes. The vertical asymptotes are at -2 and +2. So you look at the x values that would make the function undefined because they would make the denominator equal 0. And those values at this point are the vertical asymptotes. So this one, I don't have to factor it. It's just one factor on the bottom. And so here I'm going to say that the vertical asymptote is x equals -3. Same thing for these last two. These are pretty easy. They don't need to be factored. So x equals -2. Vertical asymptote for this one, x equals 1. So vertical asymptote is pretty straightforward. For the next three, we have the degree of the numerator is less than the degree of the denominator. The degree of the numerator is the same as the degree of the denominator. The degree of the numerator is greater than the degree of the denominator. Those are the three different ways that we can figure out what the horizontal asymptote is or oblique asymptote. So first, the degree of the numerator is less than the degree of the denominator, then the x-axis is a horizontal asymptote. So the horizontal asymptote is y equals 0. If the degree of the numerator equals the degree of the denominator, then the horizontal asymptote is determined by the ratio of the leading coefficients. Equal leading coefficient over leading coefficient. Okay, and then last, if the degree of the numerator is greater than the degree of the denominator, use division to write as a quotient plus remainder over divisor. So this is where you have a slant asymptote. So degree numerator greater than degree of denominator. Oops. We're going to use long division. And we're going to get y equals mx plus b. So we have a horizontal asymptote, slant asymptote. 3 scenarios. Okay? So we're going to go through each of the examples and figure out which of the 3 scenarios they are. So we look at the leading coefficient, we look at the degree of the numerator, we look at the degree of the denominator. So we are looking at the problem before it is factored. We're looking at the problem before it's factored. These ones didn't have to be factored, so we're just looking at these first. Okay, so the degree in the numerator is a 1. The degree in the denominator is a 2. So the degree in the numerator is less than the degree in the denominator, and so the horizontal asymptote is y equals 0. All right, next. The degree in the numerator is a 1. The degree in the denominator is a 1. Those are the same. If the degree in the numerator and the degree in the denominator are equal, divide the leading coefficients. So we have a horizontal asymptote, and we have y equals 2 divided by 1. Y equals 2. All right, for this one, we have a degree of 2 in the numerator, a degree of 1 in the denominator. The degree in the numerator is greater than the degree in the denominator. We have to do long division. We're going to have a slant asymptote with an equation of y equals mx plus b. So we have to do long division, and we're going to have a slant asymptote. So I'm going to do 2x squared plus 3x minus 5 divided by x plus 2. And this is the reason that I told you guys I'm teaching you polynomial long division and not just synthetic division, because this is a pretty simple example, but later on you're going to run into problems that have slant asymptotes. You're going to have to do polynomial long division. So x multiplied by what is 2x squared? That would be 2x. 2x times x is 2x squared. 2x times 2 is 4x. Draw the line, change the sign. That's a negative x. X times what is negative x? It's negative 1. This is enough to have y equals mx plus b. I do not have to finish the polynomial long division. I just have to have y equals mx plus b. So my slant asymptote is y equals 2x minus 1. All right, for the next one. 3x squared over x, the degree of the numerator is a 2, the degree of the denominator is a 1, and so the numerator is greater than the denominator, which means that, again, we have a slant asymptote, and we're going to be doing long division. So 3x squared plus 0x minus 4, because we're making sure that we have all of our exponents, and then I got an x minus 1. And again, I don't have to finish the polynomial long division. I just have to do enough to get y equals mx plus b. So x multiplied by what is 3x squared? That would be 3x. X times 3x is 3x squared. 3x times negative 1 is negative 3x. draw my line, change my signs. X multiplied by what is 3x? That would be positive 3. And this is enough for my y equals mx plus b. So I have y equals 3x plus 3. So when you look for your asymptotes, you're often going to find a vertical asymptote or even multiple vertical asymptotes for every single problem. That's very common. And then you're either going to have a horizontal asymptote or a slant asymptote, one or the other, but not both. And we'll talk about this more as we get deeper into the notes. The horizontal asymptote and the slant asymptote, they are often called end behavior asymptotes, which I don't recall seeing in our textbook, but it's something that is pretty common practice for those types of asymptotes. So slant asymptote, you might also see the word oblique asymptote. All right, next we're going to find intercepts and holes of rational functions. So you probably haven't heard of a hole on a graph before. So a hole refers to a point on the graph of a function where the function is not defined. You can think of it like a point missing from the curve. So it's going to help us to draw the curve because it's just another thing that we can draw and use to connect different parts of the curve together. And then we're also going to find the intercepts, and those are going to feel really similar to what we've done in the past. So first, to be able to find the holes of the graph, we have to take the equation of the rational function and look at it in factored form. So for this first function, the numerator does not need to be factored, but the denominator is x squared minus 9, which we can factor using difference of squares. So that's x plus 3 and x minus 3. And the whole of a function is where the function is not defined. And so x minus 3 over x minus 3 is going to be where the function is not defined, because if we were to plug in positive 3, we would get 3 minus 3, 3 minus 3, which would give us 0 over 0. And 0 over 0 isn't a number. That doesn't work. You can't do that. So we're going to say that the whole occurs at an x-coordinate of 3. And then to find the y-coordinate, you just take the resulting equation after you have canceled that factor out. So whatever factor cancels tells you the location of the x-coordinate of the whole. The y-coordinate of the whole you get from looking at the remainder of the function once you've taken that factor out and then plugging in that x value. So if we have 1 over 3 plus 3, this would be 1/6, and so that's the y-coordinate of the whole. Once you have figured out where the hole on the graph is, then you can go ahead and find the x-intercepts and the y-intercepts. Y-intercepts, sorry, there'd only be one of those. So for the x-intercepts, you would look at whatever remaining factors you have in the numerator. X-intercepts are found when the function equals 0, and a fraction can only equal 0 when the numerator is 0. So we don't have any other factors for this particular example. The numerator equals 1 when we take out that factor, and so there's no way for this numerator to equal 0. So I'm going to say none. But we'll be able to see some examples where we do have some x-intercepts after figuring out where the hole is. After this, we're going to look and see what the y-intercept is. The y-intercept is what you get for the y-coordinate when you have plugged in 0 for the x-coordinates. So I'm going to go back to the standard form of the equation, not the factored form. And if I plug in 0 for x and plug in 0 for x, I'm just going to be left with these two numbers here, -3 divided by -9. So if I plug in 0 for x, I get -3 over -9, which is positive 1/3. And that's the y-intercept. All right, so let's try this next one. We need the factored form of the equation to see if there's any factors that cancel. So in the numerator, we have a GCF of x. That leaves us with x squared minus x minus 2. In the denominator, we have a GCF of 4x, which leaves us with x plus 3. And then we have what multiplies to -2 but adds to -1, and that would be -2 and +1. Okay, so for this particular problem, the factor that cancels is the GCF of x, not the 4, just the x. So these x's cancel, which means that the whole has an x coordinate of 0. So then to find the y coordinate, we're just going to take the remaining equation and plug 0 in for x. So 0 minus 2 is -2. 0 plus 1 is 1, 4, 0 plus 3 is 3. So that's -2 over 12, which is -1/6. Okay, for the x-intercept, we're going to look at the x values that would make the numerator equal 0. A function always equals 0 when the numerator, a rational function equals 0 when the numerator equals 0. So we have two x-intercepts here, +2 and -1. +2, -1. We get the y-intercepts when we plug in 0 for all the x's and look at the numbers that are remaining. So if we plug 0 into all of these, we would end up with 0 over 0, which you can't do. And so there are no y-intercepts. And this makes sense because the whole 0, -1/6, is actually on the y-axis. That is the y-intercept, and it's a point that's missing from the graph. So the y-intercept is a whole in this case. All right, let's look at a couple more examples. So again, we have to factor. So on the top, we have a GCF of 2 that we can take out. X squared plus 7x plus 12. And then in the denominator, we've got two numbers that multiply to 6 and add to 5. That'd be 3 and 2. On the top, we have two numbers that multiply to 12 that add to 7. That would be 3 and 4. So if we look at the factors that cancel, that would be x plus 3. And so the whole has a location of x equals -3. If you plugged in a -3, you would end up getting 0 over 0. And so that's why that graph is undefined at that point. To find the y-coordinate of the whole, we're just going to take the function and plug in -3. So we're going to have 2 right here, this 2, and then -3 plus 4 is 1. -3 minus 2, sorry, -3 plus 2 is -1. And so that's a y-coordinate of -2. All right, and then our x-intercepts are where the numerator is 0. So this doesn't help us at all, but we are going to have an x-intercept here at -4. And then y-intercepts are what you get when you've plugged 0 in for x and you look at the leftovers. So 24 over 6 is 4. Okay, let's do it with this one. So in the numerator, we have a GCF of x and then x plus 2 left over. In the denominator, we have a GCF of -1 that we can take out. X squared plus 5x plus 6. And then this is exactly what we factored over here, what multiplies to 6 but adds to 5. And that was 3 and 2. So the x plus 2's cancel. So that tells us that the whole is located at an x value of -2. And then to find the y coordinate, we're just going to take the remaining function and plug in -2. So -2 in the numerator, and then -1 times -2 plus 3 is 1. So the y coordinate is 2. To find the x coordinate, I'm just going to look at the leftover factor on the top, which is just a plain x. And so the x-intercept is just x equals 0. And then for the y-intercept, we look at the function if we were to plug in 0 everywhere. So if we plug in 0 on the top, we get 0. And then plug in 0 on the bottom, you get -6 left over, and 0 divided by -6 is 0. So it makes sense that it goes through the origin, the curve does, and so 0, 0 is an x-intercept as well as a y-intercept. Okay, so to graph a rational function, first determine the asymptotes and draw them as dashed lines. Find any intercepts and plot the points, find any holes and draw them as open circles. So that's all the stuff that we found. That's all that we've done so far. Then plot any additional points as necessary to determine how the graph approaches the asymptotes. So sometimes between the intercepts and the holes and the asymptotes, you have enough to understand what the graph will look like. Often you won't. You'll have to plug in a few more points to make sure you can draw the curve correctly. And then from there, draw the curve through the selected points approaching the asymptotes. So we know that curves get closer and closer to the asymptotes, that their distance between the curve and the asymptote approaches 0. And so we want to make sure that when we draw these graphs, that's what they look like. Okay, so I made this little graphic organizer for you that can kind of help you trigger your memory a little bit for how to find different things, and if they are helpful to get from the factored form, they're kind of on here on this side, and then if they're helpful from the original equation, they're written over here. So here's our original equation, x over x to the third minus 4x, and we're just going to find all the information that we learned how to find, and then we're going to take that information and convert it into a graph. So for the original equation, we know that we can find the y-intercept, and we can determine whether the graph has a horizontal or a slant asymptote. So first, I'm just going to look at the degree of the numerator and the degree of the denominator. The numerator is smaller than the degree of the denominator, and so that means that there is a horizontal asymptote, and the horizontal asymptote is y equals 0. I can also find the y-intercept. The y-intercept comes when I plug in 0 for x. So if I plug in 0 for x, I end up getting 0 on the top and 0 on the bottom. And 0 divided by 0 is undefined, and so there is no y-intercept. All right, let's go ahead and look at the factored form. So there is no way to factor x. I'm just going to leave that there. For the bottom, I'm going to have a couple steps for factoring, so I'll start factoring it up here. I have a GCF of x, and then an x squared minus 4 left over. And then this is difference of squares, so I'm going to have x, and then x plus 2, and x minus 2. All right, so if I look at this, I can see x over x, this is a hole in the graph. And so we have a hole at an x coordinate of 0. And then to find the y coordinate, I'm going to take 1 over x plus 2, x minus 2, that's the remaining function, and I'm going to plug 0 in for x. So 1 over 0 plus 2, 0 minus 2, so that's 1 over -4. So this is -1/4. Okay. The vertical asymptotes are where the denominator is 0, not the holes, because those are holes. So vertical asymptotes are going to be at x equals -2, x equals +2. X-intercepts are where the numerator is 0, where the function is 0, and there's nothing else left in the numerator for me to make equal 0, so the x-intercepts are none. And then for the domain, this isn't really going to help you sketch it, but a lot of times when we are learning how to graph these, they'll ask you what the domain of the function is. And so we just look at the bottom and we say what x values we can't have, and that helps us write the domain. So I can have all values for x except for 0, -2, and +2. So I can have anything but 0, -2, +2. So I'm going to say -infinity up to -2. -2 to 0, 0 to +2, and then +2 to infinity. So this is how you write all numbers but skip -2, skip 0, skip +2. So all the numbers, skip -2, skip 0, skip +2. All right, so now we're going to go ahead and graph this. We have a vertical asymptote at -2. We have another vertical asymptote at +2. We have a horizontal asymptote at 0. And there's a hole at 0, -1/4. All right, so this is all that we have so far. That's not enough to graph this. And so what I'm going to do is start plugging numbers in for x to see what some other y coordinates are, x and y coordinates are, so I can graph this. So I'll do like -1. And I've got x over x to the third minus 4x. So if I plug in -1, I get -1/3. If I plug in 1, I'm probably going to get +1/3. Nope, I mean -1/3. There we go. So there's a little bit of symmetry here. I could do -1.5. -0.6. So it looks like it's going down, and then it's gonna, I didn't hit that point at all, but it's gonna go down and then follow the asymptote like this. Okay, so that's the middle part. Let's try -3. -3 is 1/5. Let's try -4. (1/12). I think it's closer. Okay, so I'm gonna expect something like this then. Okay, let's try +3. 1/5. Okay. There we go. So this is the only point that I had. It was a hole on the graph, and I just plugged in some more points so that I could see how I was going to follow the asymptote. I know that the curve is going to get closer and closer and closer to the asymptote. I just don't know exactly how it's going to do it. Okay, let's try the next problem. All right, so this one says 4x over x plus 1 squared. So that's the factored form. So we know the vertical asymptote is at x equals -1. There are no factors that can cancel, and so there's not a hole on this graph. To make the numerator equal 0, that would just be from plugging in 0. So the x-intercept is at 0, 0. For the domain, I just have to skip -1. So I'm going to say infinity to -1, -1 to infinity. So that's how we write that we're going to skip a value, skipping -1. And then over here, I'm going to need the equation not in factored form so that I can figure out the other answers. So I'll FOIL out x plus 1 times x plus 1. So x squared plus x plus 1. Okay, so 4x over x squared, the degree of the numerator is smaller than the degree of the denominator. So this is a horizontal asymptote of y equals 0. For the y-intercept, when I plug 0 in for all the x's, I'm going to have 0 on the top and 1 on the bottom. And so that's just 0 for the y-intercept. Okay, so I have a vertical asymptote at -1, horizontal asymptote at 0, and the point 0, 0 is on the graph. And you'll notice, so this is one of those unique situations where we are crossing an asymptote. So 0, 0 is right on top of the asymptote. I need to find some other points because right now I know that I should have the curve going closer to the asymptote. I just don't really know how it should look. So I'm going to plug in 1. And it was 4x. 4x over x plus 1 squared. Okay, so when I plugged in 1, I got 1. When I plugged in 2, I got almost 1. So it's going down. Let's plug in half. Oh, not half, -half. I wanted a point over here to see what was happening over here. Okay, ooh, -8, that's like way down here. Ooh, way down there. So it's going down like that, and then it comes down, and then it levels out, it looks like. You'll find that if you have a graph that does this, where it goes through an asymptote, it's pretty common for it to go, well, not common, but if you go through an asymptote, I've seen it often that in this rare situation where you do go through an asymptote, it goes up and it goes like bloop, and then it smooths out and goes down again. So if you're going to have a situation where you go through an asymptote, this is probably what that part of the graph is going to look like. I don't see graphs going through the asymptote very often, but if they do, that's something to watch out for. We need some points over here, so I'm going to plug in -2. If you're wondering why I haven't just graphed it, it's because in theory we're graphing this by hand, which means I shouldn't be using a graphing calculator. But that's what I have, and that's what I'm assuming a lot of you have. And so that's why I'm doing it this way, is I'm showing you how to do the problem without, you know, quote unquote cheating. I do not know what that is. Almost -2. Okay, so this one, this one's underneath these two asymptotes, and they'd get closer and closer to the asymptote, but kind of off the screen where we can't really see them. Not off the screen, but off of the graph paper. Okay, here's the next one. So we have the original equation, 2x squared plus 3x minus 5, x plus 2. All right, so this situation, the degree in the numerator is 2, the degree in the denominator is 1. This is a slant asymptote, and so we have to do long division. So we have 2x squared plus 3x minus 5 over x plus 2. So x multiplied by what is 2x squared? That would be 2x. 2x times x is 2x squared. 2x times 2 is 4x. Draw the line, change the signs. X multiplied by what is negative x? That would be negative 1. And then we're done. We have our slant asymptote. Y equals 2x minus 1. The y-intercept is if you plugged 0 in for all the x's and then looked at the remaining numbers. So negative 5 over positive 2. So negative 5 halves. And then for this side, we're going to look at the factored portion of the graph. We're going to look at the equation in its factored form and then see what all the other answers are. So this is a problem where you can use slide divide or guess and check or the box method, whatever method you're comfortable with using. So if you did slide divide, you would have two numbers that multiply to negative 10 and add to 3. And that would be 5 and negative 2. And then since we slid the 2 over, we're going to divide by 2. And that would give us 2x plus 5 and x minus 1. So since none of these factors cancel, there are no holes. This leftover denominator, this factor in the denominator, is a vertical asymptote. And then these two factors give us x-intercepts. So we have an x-intercept at positive 1 and an x-intercept at negative 5 halves. And then the domain, we are only skipping the value of negative 2. That's the only value that makes the denominator 0. So I'm going to say negative infinity to negative 2, negative 2 to infinity. Okay, so for my vertical asymptote, I'm going to draw in a vertical dotted line at negative 2. And then for my slant asymptote, 2x minus 1, so there's my y-intercept. Here's my slope of 2. I'm not going to connect these with a solid line. I'm going to connect them with a dashed line. Okay, so there's a y-intercept of negative 5 halves and an x-intercept of negative 5 halves and an x-intercept of positive 1. So this one might be kind of simple to draw. I could get another point, but it's probably going from here and following this part of the curve. And then down here, it's probably following the asymptote down this way. I bet it looks like that. Let's maybe look for some more points. So I'm going to try plugging in negative 1 and see what I get. Negative 6, negative 1, negative 6. Yep, that fits. What I was drawing was working. I'll plug in 5 and see what I get. I don't know that. Yeah, it's about, I should have been a little closer to the asymptote. So that's looking pretty good. Okay, so this curve is looking great. I'm guessing this other curve probably does a similar thing on this other side. It's probably going to go like this down here and then just get closer to the asymptote over here too. Something like this. So let's plug in negative 4. Negative 15 over 2, negative 4 is negative 7.5, yeah. Okay, so it looks something like that. Okay, so to sketch the graph, just a reminder, you're going to find all this information, and you're going to graph all this information. And then after that, you're going to probably have to add some additional points, and just keep in mind that the curves have to go closer to the asymptotes. So I shouldn't see any random graphs. You'll notice too, I was taking time with the graphs. I was trying to draw the points accurately. To get credit for this in a testing situation, you have to have graph paper, and you have to have accurately drawn points. So this is already a sketch. A sketch is an approximation, but not perfect. This is as imperfect as I would let you guys draw in a testing situation to get credit. So anything that's not on graph paper, or anything where I can't tell that you understand that you're approaching the asymptote as you draw the curve, none of those would get credit. So that it would have to be pretty similar to these drawings to be able to get credit. Also in a testing situation, I'm not going to make you draw 5 of these. So you should be able to find this information, but it's not something that I would make you do repetitively. All right. So next we're going to look at how to solve rational inequalities. And when we solve rational inequalities, typically we're not going to draw a graph, because you guys just saw how kind of tedious drawing the graphs are. And it takes a lot of extra work. So we're going to solve rational inequalities by using the sign charts or using the test points. Two different ways of explaining the same thing. So first, you're going to make sure that the inequality is 0 on one side, and then you're going to make sure that with your rational expression you only have one fraction. That's it, just one fraction. And then you're going to solve that rational expression so that you know what factors make the numerator equal 0, what factors make the denominator equal 0, because then you'll know all the x values you have to avoid, that's the ones on the bottom, and all the x values that are 0, those are the ones on the top. And then from there, we're going to go through and do a sign chart. So this is just something you can kind of fall back on if you need to look at the instructions again. So let's go ahead and try it with some examples. So this one does not equal 0, and so we're going to have to subtract the 2 over to make it equal 0. And then this rational expression is not a single fraction, and we need it to be written as a single fraction. And so for this whole number 2, I'm going to have to get a common denominator with this fraction over here. So I'm going to write this as a fraction, 2 over 1. And then to get it so that these two terms have a common denominator, I'm going to multiply this fraction by x minus 2 on the top and x minus 2 on the bottom. So now we have a fraction with a common denominator. We have x minus 2, and we can go through and do this calculation with the subtract 2 times x minus 2. So I'm going to write my denominator, and then in my numerator I'm going to say x plus 3 subtract 2x minus 4. So I just took the 2 and distributed it. So x plus 3 minus 2x plus 4. And then I can go ahead and combine like terms. So I have a negative x and positive 7. So if I could imagine this as a graph, this would help me find my x-intercept. That would be where the graph equals 0. This would help me find my vertical asymptote. That would be a value that the graph cannot have. So I'm going to draw these on my number line. I'm going to have this negative. I'm going to take out the negative, just because that's a little bit closer to how I'm used to seeing this. And then x minus 2 So I've got 7 and I've got 2. Now 2 is a number I absolutely can't have. That number is a vertical asymptote of the graph, can't have it no matter what. The 7 is an x-intercept. I can only use the x-intercept as one of my answers if my inequality says equaling 0 is okay. And in this case it does. So I'm going to take the 7 and fill it in. And then I'm going to choose values to test. So 0, 3, 8. I'm just choosing values that are inside these different intervals. And then I can go ahead and test them. So I've got a negative sign. 0 minus 7 is negative. 0 minus 2 is negative. So for 0, I've got a positive number divided by a negative number, which is negative. All right, for 3, I've got a negative. 3 minus 7 is negative. 3 minus 2 is positive. So I have a positive divided by a positive, which is positive. And then last, I've got a negative sign. 8 minus 7 is positive. 8 minus 2 is positive. So I've got negative divided by positive is negative. And then I just have to look at my inequality and see what sign described the correct answer. So was it less than 0 or greater than 0? These answers were less than 0, and so we're thinking of the negatives as the answer. These are the answers right here. So I'm going to say negative infinity to positive 2, not including the 2, and then 7 to infinity, but I'm going to include the 7. And that's the solution for my rational inequality. Okay, let's try this next one. So again, I have to make it equal 0, so I'm going to take this fraction and just subtract it over. And then I have to take those two fractions and I have to write them as a single fraction, a single rational expression. And so I need to have a common denominator between the two fractions. So this fraction has an x plus 3, but it does not have an x minus 1, so I'm going to multiply it by x minus 1. This one has an x minus 1, but it does not have an x plus 3, so I'm going to multiply by x plus 3. So for our common denominator, we have an x plus 3 and an x minus 1. And then for the numerator, we have a 2 times x minus 1 minus a 1 times x plus 3. So this is 2x minus 2 minus x minus 3 2x minus x is x, negative 2 and negative 3 is negative 5. Okay, so if we were to graph this, this would have an x-intercept at 5, a vertical asymptote at negative 3, and a vertical asymptote at positive 1. The vertical asymptotes you can never equal. Those are values that are excluded from the graph always. The x-intercepts you can only equal if your inequality says equal to 0, and in this case it does not. So I cannot equal the x-intercept in this situation. All right, now what I'm going to do is choose some points to test. So negative 4, 0, 2, 6, and then I'm going to check the signs. So negative 4 minus 5 is negative. Negative 4 plus 3 is negative. Negative 4 minus 1 is negative. A negative over a positive is negative. 0 minus 5 0 plus 3, 0 minus 1. A negative divided by a negative is positive. 2 minus 5 is negative. 2 plus 3 is positive. 2 minus 1 is positive. A negative over a positive is negative. 6 minus 5 is positive. 6 plus 3 is positive. 6 minus 1 is positive. So that's positive. Our inequality tells us that we are looking for answers that are greater than 0. And so they are here and here. And so our interval is from -3 to 1, not including the ends. And 5 and beyond, not including the 5. All right, last one. So we're going to make this so that we have 0. I need a common denominator. And so I'm going to take this fraction and multiply by x plus 8 over x plus 8. And this would be 2x plus 16. Four x plus 16. So I can factor that in the top to see what the x-intercept would be. Okay, so on this graph, I have an x-intercept of -4 and a vertical asymptote of -8. I can never equal the vertical asymptote. The x-intercept of -4 I can equal only if this says equal to 0, and in this problem it does, so the -4 can be part of the answer. I'm going to choose values to plug in. And so here's where I'm plugging them in. Okay, so 4 is a positive number. -9 plus 4 is a negative. -9 plus 8 is a negative. So that's going to be a positive. Negative over negative is positive. 4 is a positive number. -5 plus 4 is a negative number. -5 plus 8 is positive. So that's negative. 4 is positive. 0 plus 4 is positive. 0 plus 8 is positive. Okay? And our answer is the sign that is less than 0, and so that's right here. So it's -8 to -4, including -4, not including -8.